There.
Hello.
Can you share your screen, William?
I won't actually share. If you could just close your share and spotlight me, please.
I'm not sure.
Thank you very much, John. Great pleasure to be here, and I'm looking forward to talking a little bit. Just to get a few seconds background before I begin, I work with Papworth Construction testing equipment. We're expert suppliers of structural and geotechnical instrumentation, corrosion investigation and monitoring equipment, and a very wide range of inspection and test equipment out on site for civil and structural applications. What I'm particularly going to be talking about today is on the corrosion side, because structural health monitoring tends to have a great focus on units of strain, dynamic, fast measurement of sound or acceleration or motion. And I sort of want to step to other aspects of monitoring a structure, which is a little bit more on the durability side. So my presentation today is going to be on the corrosion monitoring of concrete structures, which are new and old. Particularly relevant to everyone here from PCTE is we've got various supplies of instruments. We work with Geosense for our vibrating wire sensors, as John mentioned. We also have corrosion monitoring equipment from Force and sort of specific bus-based instrumentation data logging from Protector. But this is all sort of input to the main work of structural health monitoring. So on today's presentation, it's explicitly going to be about what I mean when I say corrosion of a concrete structure. So I'll go quickly through the life cycle of steel reinforcing in concrete, why it corrodes and what it does. Then I'm going to point out various opportunities to use sensors you may be familiar with or sensors that you're not familiar with to catch lightning, sort of catch the moment something meaningful happens. So the first thing to understand about steel and concrete is that they form a perfect pair. The chemical environment of concrete is very basic, high pH, which creates a oxide layer on reinforcing steel in this environment, very similar to the oxide layer that forms on aluminium and air. So this helps to ensure that steel is durable and won't corrode in concrete when cast. So we're talking about rust, particularly rusting of steel. We need a certain chemical environment to deal with that. So we need water and oxygen for the corrosion reactions to occur. But water and oxygen alone aren't going to be enough to promote corrosion because we have that protective layer on the steel. But first thing is, if we can stop that water, dry out the slab or other concrete element, or we can somehow stop the oxygen, it's going to either change or halt the corrosion reaction. So let's talk about what can cause corrosion. The two most common external environment sort of contaminants that can make their way into the concrete is chloride ions and carbon dioxide. Carbon dioxide forms an acid, and chloride ions will form an acid and will also promote and accelerate corrosion. But in order to do that, they need to reach the level of the reinforcing steel. And this is the first step in the life cycle of a concrete structure. Now, for my example, I'm going to be talking primarily about chloride ingress. So think a bridge or marine structure exposed to salt water. And the first protection of that structure is how long it takes for those chloride ions to diffuse from the surface to the level of the reinforcing steel. Then it will break down the protective oxide layer, lowering the pH, and our oxide layer will be stripped away, and it will promote what we'd call pitting corrosion. So you've got localized regions of corrosion activity and protected regions where you have a cathodic region and an anodic region. Current will flow between the cathodic regions and the anodic regions. Cathodic region will be protected and will not corrode. Anodic regions will see corrosion occur. Rust or corrosion product will form. And then we're going to start to get the physical results of this corrosion activity. We're going to begin with cracking and eventually damage, spalling, and breakdown of the concrete. So that's the life cycle of corrosion in concrete for this particular mechanism. You begin by the external world making its way to the level of the reinforcing steel, a protective layer and protective environment being stripped away, active corrosion beginning, and then that active corrosion causing increasingly large physical damage. It's only once you've got quite considerable physical damage you can spot the corrosion in your structure. So if we're going to talk about structural health monitoring or even inspection of a structure exposed to corrosion, we need to catch when things start, not when they end, because at this point, the repair is incredibly expensive. You've got to somehow remove the chloride contaminated concrete or apply cathodic protection to stop corrosion electrically. And you've got to repair the physical damage. So let's talk about a tool you probably are familiar with, which is appropriate to catch the physical beginning of damage. And that would be some form of acoustic emission. This is not an area I have a great deal of expertise, but I did want to point out that if you are using something like acoustic emission, you'll be catching physical damage as that reinforcing steel undergoes expansive corrosion. And that's right at the end of the durability cycle. Damage has begun to occur, the concrete is contaminated. It's still a difficult repair, though the extent of the corrosion may be less. So let's keep winding back in time. Let's see what we can capture if we take into account, rather than a physical sign of corrosion, let's talk about an electrochemical sign of corrosion. So we know we have a chemical reaction occurring, and we know we have current flowing between various points on the concrete structure, which means we can actually start to take electrical measurements to evaluate condition. Now, I've just put a very simple illustration of a voltmeter here to show the principle of using potential measurement or half-cell potential measurement. I've placed a sensor I'll describe in a second close to the physical reinforcing undergoing corrosion, and I've made an electrical connection to that reinforcing steel, measuring voltage. I could also, with the same physical connections, measure current. Both of these provide a measure which can be used to evaluate, is corrosion happening near to our sensor? So this is a very common tool used in inspection. In the illustration here, it's just a quick explanation of half-cell potential measurement or half-cell potential mapping. This is done from the surface of the structure, and measurements are taken spatially, so over a meter or 2 meter or 3 meter or 30 meter area, measuring physical voltages over that area and looking for deviations from a general value. So in this case, the values would be dropping from around minus 150 millivolts to minus 300 or minus 400 millivolts, close to that corrosion hotspot. So that's measurement in space, finding active and passive regions on a structure. This is a very common technique. Now, we're talking health monitoring, we're talking data logging. So what can we do? We can take the reference electrodes and we can put them into the structure. This is also the way that they monitor the performance of cathodic protection systems. So looking at that, this is a reference electrode which might be used to measure from the surface, and this is embeddable reference electrode. They both have the same function, which is to be half a battery. The other half of the battery is the reinforcing steel, and we measure voltage between the two. So if we now start recording voltage and time rather than voltage and space, we can get a chart like the following. So that chart is just, in this case, I'm showing current rather than voltage, and there's a distinctive increase in voltage as regions being monitored begin to corrode. So the red line shows activated and corrosion activity beginning first at about the 46 days mark on an accelerated exposure, and then about the 45 days mark for the green, about the 48 days mark for the red line here. So essentially catching when corrosion begins electrically. So now we get it before physical damage is done. That's good. Let's keep winding time back further, because what we'd really like to capture is when corrosion begins at is sort of what causes the corrosion and how long it's going to take. Because then we can start to adjust our durability models. If you've got a 100-year design life on your structure, a big part of that calculation is how long it takes the outside world to get in and damage it. Now, first option is you think, oh, we could just put some sort of sensor in for pH. I'm not currently aware of any direct pH sensor for use in concrete structures. So let's take that one off the table and let's start to be a little more clever. Well, we said that we need to have water, we need to have oxygen at the level of the reinforcing steel. We can't directly measure these parameters, though we can use something like a relative humidity sensor for moisture, which may be appropriate. We could also measure conductivity, which captures the presence of water, presence of chloride, because that'll make a more conductive concrete as well, presence of carbon dioxide, again, increasing the conductivity. This is one way we can evaluate. It's a little bit unsophisticated, but it does catch if that concrete environment is going to promote corrosion. And then we can continue to be a little more clever than that, because again, what we really care about is how long it takes for that concrete to become contaminated and promote corrosion. So we can't directly measure chlorides, we can't directly measure carbon dioxide, but we've already got an approach. We've evaluated, we can measure the beginning of corrosion electrochemically, so we can introduce more reinforcing steel. This is a representation of a chloride probe. So we now have a reference electrode embedded with several additional pieces of steel, which will begin to corrode because they're closer to the surface before the main reinforcing steel bar. Practically, a system may look like this. The one on the right would be a ladder probe. The one on the left is a Corrowatt system from Force with a matching reference electrode. And these all work the same way. The chlorides diffuse from the surface. When they reach the level of the reinforcing steel, things begin to corrode. So you can see that here. We have the different heights of bar. Chlorides will reach the steel. Corrosion will begin, can be electrochemically measured. So this practically gives us the time of initiation. And finally, we can reevaluate our design calculations. If we estimated it would take 50 years to see the reinforcing steel begin corroding, and it actually took us, with new calculations, 30 years, well, we need to do something to slow down that diffusion. And we can take that action at much less cost before any steel is damaged or even at risk of damage. Now, tools like this are not confined to use on a new structure. It is possible to retrofit equipment like this. This is a representation of a Corrowatt system, again from Force, physically able to be embedded at varying depths into the concrete surface.
Ding.
And can now be retrofitted into place. And just to give a quick example of the output from a system like this, we have, again, in this case, this is voltages being presented, so looking for a variation in voltage between corroding and non-corroding regions. So several regions over time showing a higher potential difference, higher voltage, several showing lower, a few in between. So a clear separation between regions that may be corroding and regions that are not corroding. So that's just a quick presentation on sort of indirectly measuring properties.
All right, thank you very much, William. I think that really good to sort of think outside the box of having to do everything with something weird or something really, really difficult, and great to be measuring something so simple as potential as an indication of health. I think that's a really good thing to kind of keep the focus on. Again, to anyone who's thinking about measuring something on civil structures, good to have a chat with William. They've got all sorts of tools, all sorts of widgets, and happy to go out there. So
thank you, John.
My